canal and it will create problems. So that was the problem in the design of, say, lined canal. And when we talked about design of unlined canal, then again there may be two different type of formation through which the channel is moving. Say one can be non-alluvial and other can be alluvial. So when it is alluvial channel, or first let us talk about when it is non-alluvial channel, then the question of getting eroded, this will be coming when the velocity exceed a high level. That is, there is always a maximum permissible velocity, and we should not allow the velocity to be higher than that maximum permissible velocity. So that was the design consideration, because sedimentation, the problem of sedimentation is little less than the problem of, say, scouring in case of non-alluvial channel. But in case of alluvial channel, and of course we did discuss about that earlier, and in case of alluvial channel, the problem is much more than the design of non-alluvial channel, because in alluvial channel, as you can see, that there is a problem of scouring of the channel by the flowing fluid, as well as there is the problem of sediment deposition in the channel. Now, if sediment get deposited, then also there are problem. If sediment, suppose if the channel gets scoured up, then also there is a problem. As such, the very design principle is that we should try to have a velocity which is of the type that non-silting, non-scouring. Of course, in true sense, it is very difficult to get a velocity of that type. In reality, there will be scouring to some extent, there will be sedimentation to some extent, and it will be in a balanced position, and apparently it will be appearing like that this velocity is causing no scouring or nor it is causing any deposition. And that particular velocity we call as critical velocity. And here we should again remember here we should again recall that we did discuss about critical velocity when we were discussing critical flow condition, and that critical velocity is different from this critical velocity. And for designing of this alluvial channel, we have different methods. Say one is Kennedy's method and another is Lacey's regime theory principle. So these two methods also we did discuss in our last class, and Kennedy's method we completed almost, and Lacey's theory we were discussing the very basic steps we were to discuss, but the equation that were developed by Lacey's were discussed. And so let us start today with the steps that are involved in design of channel, that is alluvial channel, by Lacey's method. Well, so we can concentrate into the slide that unlike Kennedy's method, the Lacey's method is different from the fact that he gave emphasis on the parameter silt. That is because the erosion depends on the silt, and the sedimentation will also depend on the silt size. So he gave more important to that point, and as such, he defined a term called silt factor, and that silt factor was used in most of his equation. And that silt factor F, this silt factor F, we need to know. And then he gave one relationship for the silt factor, which we can find out in terms of MR. By MR, what we mean that it is the D50 size of the sediment, that is the sediment by which the channel is composed of, and the sediment which is coming in. Because we were discussing earlier itself that when we talk about regime channel, then we consider that sediment that is flowing into the channel, that is the sediment charge we call silt charge, that is flowing into the channel, and which the channel is being formed are of the same quality. So we are talking about D50 means both the silt. Well, then this is the D50 side, that is the size of, if we carry out sieve analysis, then the 50% finer than a particular diameter will be getting particular silt size, particular, say, sieve size, and that we refer as D50, and this is in millimeter. So we can call that where MR is D50 and it is in millimeter. Okay. So That way we can get the F size. So first step is that seal factor F is calculated from average particle size known from sieve analysis. Well, so that will be our first step. And we should be very much careful in determining this F value, because all other relation will depend on these F value. Okay. Then the second step, that regime velocity V. Regime velocity V means, we mean that is the velocity when the channel will be in regime condition. And in Lacy's theory, by regime condition we mean that channel has reached the regime condition. That means there will be no further erosion, no further deposition, and it will remain as it is. And that is the very basic principle of regime theory of Lacy's. And that regime velocity, at that condition, what will be the velocity, that we can find out. This is calculated from the value of Q. Discharge we will have to know. So because generally when we talk about design of channel, we need to design the channel to carry a particular discharge. So that Q we will have to know from other hydrological study, or if it is irrigation canal, then depending on the discharge to be supplied to the agricultural field. So that way we need to know the discharge. So from that known value of discharge, and already that we have come to know what this F value is, from the known value of F, using these two values, we can find out what velocity is, that regime velocity, by using this formula. In fact, when we were discussing in the last class, we were talking about this particular formula which was given by Lacy's, and from this formula itself we can have this relation, because if we multiply this by V, that in fact I did so in the last class also, that if we multiply it by the V, this A into V become Q, and this become V to the power 6. That way V we are getting as Q F square by 140 to the power 1/6. So that way we can get the V value. Now, once we get the regime velocity V, then for design of channel, we need to know what will be the hydraulic radius, because this V and Q, based on Q we can have the V, and from that again we can have area. But then what will be the hydraulic radius? That is also important for design purpose. And then, so hydraulic radius is then calculated. Hydraulic radius is calculated using Lacy's equation, this particular equation that we did discuss in our last class. That is V is equal to 2 by 5 FR to the power half. Well, from this we know V, we know F, so we can have what is hydraulic radius. And what hydraulic radius is, if somehow it is not in memory, then it is nothing but A by B. So that we need to find out. And A is nothing but, it is a function of bedwidth B and Y. And of course, if it is a trapezoidal channel, then side slope Z is also coming here. And of course, the Z in Lacy's theory, we keep a fixed value, that is 0.5:1 is normally kept. That is for regime condition, it is considered that Z will be 0.5:1. So by that Z we move. So that's why I'm writing this as A is equal to a function of B and Y, and P is also a function of B and Y. So we have two unknown, and we are getting one relation which is giving us actually the value of A by P. If somehow we can get the value of A and P separately, then our task is over in a sense, because now we'll be having two equations. If we can have A and P, we'll be having two equations of B and Y and two equations. So from that two equations, we can solve for two unknown B and Y. So now let us see how we can have that. Well, so sectional area A, we have R with us, the sectional area A, and the perimeter P is calculated by using continuity equation. Also we can apply it, because Q is equal to area into velocity. So already we have got the velocity term. So we know Q, so we can find area directly. Or we can use this sort of equation also. This is also one equation that is given by Lacy, that is AF square is equal to 140 V to the power 5. In fact, these are all related equations. So if we use this equation, then also we can find out what the area is, or from continuity equation we can find what the area is. And that we can calculate directly. And then P we can calculate by using this particular equation. P is equal to 4.75 root over Q. Well, So Q is known, that's why we can find out P. Now here I want to emphasize one point, that these coefficients that we are writing here, that is P is equal to say 4.75, that value is actually, this equation rather itself is a derived equation. Original equations were given by Lacey's, and from that we derived this equation. And so this coefficient 4.75 is not exactly 4.75. And that's why there are some say round off made in this part. And another important point, that originally this formula were developed in FPS system, and then it was converted to as say our meter second system, MPS system. So that way, in this conversion also we always introduce some amount of error. So anyway, but still when we are doing our design purpose, say finally we are getting our design section. I mean, why this is not that important, again I would like to say that point, because suppose practically we are designing a channel and we are getting our channel dimension as say width is suppose 3.39 or 3.38, something like that, then people will prefer to have a width in practical condition. If you go to the field to make a channel of width 3.38 or something like that, it is very difficult. So what will be made? It will be made say 3.5 rather than making 3.38 or 3.39 or 3.34 even. So people can go for 3.5 meter. So that way, always we will be rounding up our design dimension at the end. So if we round up here itself by small amount, that is not making that much harm, or that is not making gross difference in our ultimate result. And so we use this equation. So P is equal to 4.75 root over Q is the equation which is used for calculating the perimeter. Now, after calculating the perimeter, after having the area, what we can have now, that from the known value of P and A, this depth and width of the channel can be computed directly. So that is one advantage. Directly means here again we need to know one point, that we are calculating it directly considering side slope as 0.5:1, which is generally taken from the concept of resigned channel, and it was suggested. So by taking this as 0.5:1, we can calculate our dimension of the channel. Well, so what is the advantage or computational advantage in this particular method till now? What we have done, that in Kennedy's theory, if we remember, we had to go for trial and error procedure. That is, we get a velocity, say non-tilting, non-scoring velocity by Kennedy's theory, that is V is equal to say 0.55, then depth to the power 0.64. So from that sort of equation we got a critical velocity. Of course, then later on he introduced a coefficient m, a multiplying coefficient m again, which take care of about that silt size. So that way we were getting that velocity. Then based on that velocity we calculate the dimension of the channel, and then after getting the dimension of the channel, getting the slope of the terrain, we calculate what the actual velocity will be by using uniform flow formula. And then this velocity, that is the uniform flow velocity, what we are getting in actual, after getting the size dimension of the channel, we can calculate for a given discharge what will be the velocity. So that velocity and the critical velocity, that is the non-silting, non-scouring velocity, we need to compare. If these two are matching, then only we consider that our design is okay. Otherwise, we need to repeat. We should consider another depth, another critical velocity we will be getting, then that trial and error procedure we need to continue. Well, and then as in some cases when B by Y ratio was given for that particular discharge, and then we can in that case adjust our slope, but that is also by trial and error procedure. Well, so but here in Lacey's theory, that trial and error procedure is not required. That's why it is directly we can calculate. That is one advantage of Lacey's equations. And then of course after designing the size, we need to know that what will be the regime slope, because as we did discuss in the last class, that a channel adjust a channel when once we allow a particular amount of discharge to flow through it, it will be adjusting its depth, it will be adjusting its width, as well as it will be adjusting its slope. And for a particular, and it will be adjusting the slope in a way that it will be in regime condition for a particular depth, for a particular width, and for a particular slope. So slope is also important here. And that's why for lattice design, we need to calculate what the regime slope is. And that regime slope we can calculate, that longitudinal regime slope is calculated by using the slope equation. S is equal to f to the power 5 by 3. Again, it is a function of f, that is the seal factor. F to the power 5 by 3 divided by 3340 q to the power 1/6. Of course, here I want to mention one important observation, that is, this is also a derived equation. This S, that expression we are getting, is also a derived equation. And if we derived it from the equation that we are using here, say this one or the previous equations that we were using, all these equations, and of course you can refer to the equations that we did discuss in our last class. So when we put all those equations, we manipulate with all those equations, and we try to get an expression for this slope in terms of Q, then the actual derivation we get the value 3455. But the value in place of 3455, this equation, in the equation of slope, people normally use the value 3340. They used to use this value, rather 3340. And now when we calculate, when we derive it with the value or the coefficient for other equations that we are getting in our MK system, and then we try to get the value, we get 3455. But still people are using this value, because with this value people could get a good result earlier. And there is another point that as I did mention, due to unit conversion, we are in rounding off these equations. Now what we are using, there are some difference in the coefficients, and then when we use this value, then this value may have some difference. And of course, one point if we notice here, then it is that q to the power 1/6, and then we are dividing by 3340. It is a very large number, in fact, 3340. And f value is a very small value. F value is a small value, and that is to the power 5 by 3 is there. So now when we talk about the slope, in place of 3340, if we use 3455, the difference will not be, the value of S, ultimately the difference in value of S will not be that much large. But still, some student, or in fact sometimes people get confused that when we derive we get 3455, but in the equation it is written as 3340. Many books are following this 3340 equation, and many books are using, or rather some books has mentioned this point, the 3455 or around 3450. So there should not be much confusion about that part, because these are derived equation, and this coefficients can always have some influence on that, what coefficients we are using, and rounding of the coefficients, and then conversion of unit, all those things are playing its role there. Then similarly, from this Q we can calculate the slope, regime slope, and similarly by using the hydraulic radius R, what we have already obtained, using that hydraulic radius R also we can calculate the slope. So both the equations will give us same value of slope, and then this slope we need to have. Now the problem is that in the terrain, if we do not have that slope, suppose in the terrain the condition is like that, we cannot have that slope, then there is a problem. We need to manipulate that. What we need to do, say if it is a very steep one, then we have to flatten it down, or we may have to take the channel. Suppose in this direction the slope is very steep, then say we can, suppose let me draw a slope. Suppose this is say from here to here, this is the slope in the three-dimensional view. Let me draw it like that. So this is the slope, and this slope is much more. Of course, if it is very, very high, then or very, very low, then it is difficult to manipulate. But to some extent, we can manipulate like that. Say if this is very large, then this one we can just fill it up and we can reduce the slope. This is one way. Another way is that if we take the channel like this, then our slope will be reduced. Slope will be flattened, because from the elevation here, suppose it is 100, here suppose it is 90, then the difference of elevation is 10 meters, suppose. And from here to here, distance, if we go by a straight path, our distance, our slope will be more. If we go by a curved path, if we increase our length, then slope of this channel will be reduced. Of course, making a curvilinear channel and a longer channel will be costlier. So in many a time, we need to compromise with this particular value, and then we may not achieve this value in practical situation. But still, we should try our level best so that we can have all this value as suggested by the formula, and so that we can really have a regime channel. Well, then after that, let us see, we have discussed this Kennedy's method, where we consider a critical velocity, and then we have discussed about Lecis method also, and where we have seen that how using the principle of regime channel we go for design of channel. But in these methods, definitely we have lots of drawback, and in fact if we use Kennedy's method, if we use Lecis method, our design dimensions are different. So now people get confused at which should be used. That of course will depend on experience, and in a particular region, suppose one formula designed by one relation is giving better result, then we should go for that particular method. And the more the information we have when we want to take care of the silt value, then more the information we have about the silt factor, then we should use that, we should go for the formula which is considering more that silt factor value, that is the Lecis theory. Well, but still, what are the limitations it have, or what are the drawbacks it have? Well, drawbacks can be many, but we are putting here, or we will be discussing some of the drawbacks which are important. Say, size of silt particles generally do not remain same from upstream to downstream due to attrition of the particles. Here we are talking about a silt grade, say D50, or say silt size. Now that silt size, even in fact if D50 is remaining same, but the distribution of silt in a mass of silt, if we collect, the distribution of silt size means the gradation of silt, that may not remain same, because